Hello, Calculus 1 student. This is the lecture video for section 2.2, which is all about the, various rules for finding derivatives. So in section 2.1, you looked at finding derivatives and went through this process of using the limit definition to find a derivative. So the derivative f prime of x is equal to the limit as h approaches 0, this is an h, of f of x plus h minus f of x over h. And so you went through this process of finding the derivative, either using this definition or the other definition. This one, f prime of a, is the limit as x approaches a of f of x minus f of a over x minus a. So what this section and the next section, section 2.3, and the section after that, like basically most of chapter 2 is about finding shortcuts so that you don't have to go through this process every time to find a derivative. So we just call these shortcuts rules. So we're going to learn various rules today. Looks like we'll look at 4 rules in this section. And then I'll talk about a concept called the second derivative. So that's the plan for this section. So in order to understand the power rule, which I will explain in a moment, or which I'll show you in a moment. In order to understand it, though, what I like to do is just to work through an example of finding a derivative using the same techniques that you used in section 2.1. So for my little example here, let me just say example, we're going to find the derivative of f of x equals x cubed. And I'm going to use this definition, this one here. I'll turn off my video so that I'm not covering stuff up. So I'm going to use this definition, the main one. And so we can say, so just using that definition, we can say that f prime of x is equal to the limit as h approaches 0 of, so for our f of x plus h in this case, like for this part, the f of x plus h, basically what that means is I need to plug in x plus h for x. So if my f of x is x cubed, right? This is my f of x, x cubed. So my f of x plus h will be, in place of the x, I put x plus h. So I'll have x plus h cubed. So for the first part of this, the f of x plus h, I'll have x plus h quantity cubed, and then minus my f of x, which again was x cubed. So this will be minus x cubed. And then this is all over h. And so go ahead and expand this. So the limit as h approaches 0. I have a little shortcut method for expanding this, the x plus h quantity cubed. If you want to see the little shortcut method, you can totally see it. If you go to our modules, and then at the very end, well, where is it? The very end, past the last week, you will see a list of proofs. And right here, I posted a proof of the power rule, which we're going to learn in a moment. But in this proof, I explain like a shortcut for expanding stuff like we're about to expand. So just FYI. Yeah. So we'll see a shortcut. So just going back to yeah, so I'm just gonna expand this without, I'm not gonna go through this whole process. X plus H times X plus H times X plus H. I'm just gonna do my little shortcut. And again, if you want to see what the shortcut is, again, watch that proof of the power rule and you will see it. So this ends up being, when I multiply all of this out, I end up getting x cubed plus 3x squared h plus 3x h squared, and then plus h cubed. So that's what I end up getting. And then minus, and then this part is just x cubed. I'm just bringing that down. And then all of this is over h. So I'll keep going. And one thing I want you to notice is that we have a positive x cubed here and a negative x cubed here, so they cancel each other out. So I end up with the limit as h approaches 0 of 3x squared h plus 3xh plus 3h x h squared, and then plus h cubed, and then this is over h. And notice that in my numerator, all three terms have an h in them, so I can factor an h out. So I'm going to factor that h out, and I end up with the limit as h approaches 0 of, so I'm factoring the h out. So I have h and then times 3x squared plus 3x. I had two h's here, but I took one away, so now it's just xh. And then for the last one, I had three h's, but I took one out, so I just have h squared there. And in my denominator, I still have my h, but now notice the h in the numerator and the denominator, I can cancel those out because any number divided by itself is just 1, and 1 times anything does not affect the value of a number. So I cancel those out, and I end up with limit as h approaches 0 of, so all I have left in my denominator, since the h got canceled out, all I have left is a 1, really. So and in my numerator, I have the 3x squared plus 3xh plus h squared. And now I can just go ahead and plug in my 0 for h, because this is just the limit as h approaches 0 of 3x squared plus 3x plus, or 3xh plus h squared. So if I plug in 0 for h at this point, I won't get 0 in my denominator. Versus if I had plugged in 0 for h in the beginning, I would have gotten 0 in my denominator. So that's why I went through what I just went through, all of this stuff. So now I'm going to go ahead and plug in 0 for my h, and I end up with 3x squared plus 3x times 0 plus 0 squared. And this part ends up just being 0, right? So all I really end up with is 3x squared. This is my derivative. One way that I can say that this is my derivative, so there are lots of different ways to say derivative. Let me just talk about the different notations for derivative before I go ahead and write the one that I'm going to use. So when you see this means derivative. This also means derivative. This also means derivative. This also means derivative. And this also means derivative. So like all of these mean derivative of your function. The way that you read these, so the first one, you're going to read this f prime of x. The second one, you read y prime. The third one, you actually just say the letters. So you say dy and then dx. That's all you do. And then this one's similar. df, dx. And then this one, you read this d, dx of f. So lots of different ways to express derivative, lots of notation. Just like in English, we might have various words that mean the same thing. Same thing happens in math. So, but the ones that I like to use the most are, I like this and I like this right here. And then sometimes this. I rarely use the other two. But for something like this, the problem that we just worked through, or that I just worked through, I found the derivative of x cubed. And so the way I like to write this is by using the last notation. And so I would say d dx of x cubed, or the derivative of x cubed, equals 3x squared. So I just found that the derivative of x cubed is 3x squared. And so if I went through the same exact process to find the derivative of x to the fourth, I'm not going to go through the process because, as you see, it takes some time and I don't want this video to be too long. But so I won't go through the process. But if I did go through the process, guess what I would get? I would get 4x cubed. And if I went through the process of finding the derivative of x to the fifth, guess what I would get? I would get 5x to the fourth. And what I'm hoping is that maybe you see a pattern at this point. So just like take a moment and guess what you think I'm going to write for the derivative of x to the sixth. I'll give you a moment. Did you guess this? Because if you did, you're correct, and you have like figured out the pattern. So if you haven't figured out the pattern, here's what to notice: that basically when you're finding the derivative, the exponent drops down to the front. And then for your new exponent, you take 1 away from what your original exponent was. So this leads us to our first differentiation rule. By the way, differentiate means, it's a verb. So to differentiate means to find a derivative. So when I say differentiation rule, I mean rule for finding derivatives. So the first differentiation rule that we learn in this class is referred to as the power rule. This is probably the rule that you're going to be using the most of all your differentiation rules. And it's that the derivative of x to the n, so this is used whenever you have a variable raised to a constant power, is equal to n. So remember what I was saying about exponent drops to the front. And then we have times x, and then raised to the power of whatever our n was, but then minus 1, whatever our exponent was minus 1. So this is called the power rule. So we are going to practice using this rule by doing a homework problem. So let's go to the homework. And let's look at number 1. So number 1 says find the derivative of 6x to the 9th minus 2x to the 5th. So what you want to do here, we're going to use the power rule, which means power drops to the front. So for the 6x to the 9th part, it's like we end up with, so I'm going to say f prime of x equals, so this is me saying the derivative is equal to, and that 9, it drops to the front. So we have 9, that will just be multiplied by the 6 that's already there. And then x to the 9 minus 1, or x to the 8th. And then minus, and then same idea with the 5. The 5 drops to the front. So minus 5 times the 2 that's already there, and then x to the previous exponent, the original exponent, minus 1. So if we multiply 9 times 6, we get 54, and then take 1 away from our power, we get 54x to the 8th minus 10x to the 4th. And this is our answer. Oops. Minus 10x to the 4th. So there we go. Let's look at number 2. Number 2 is a little bit, we have to do a little bit of work to work through this one. We're going to use the same rule, but I just want to remind you of some algebra rules that you might have forgotten. And then we'll use the same rule. And then notice it says type your answer without fractional or negative exponents. So I'm going to switch over to the iPad for this one. So for this one, the algebra rules that I want to remind you of are rules involving exponents. So one is that in general, the square root of some number, or like the square root of a, for example, is the same thing as a raised to the power of 1/2. If you have something other than just like a square root, like let's say you have like the nth root of a raised to some power, that's the same thing as a raised to the power of m over n. So you might find that useful for another problem. And then a third rule is that if you have a raised to a negative power, like a to the m, negative m, that's the same thing as 1 over a to the positive m. So we're going to use this rule right here and this rule for this problem, because notice we have situations that look like that in this problem, this example. So for example, so what I mean is that the negative 2 root x, like I can rewrite this as negative 2 times x raised to the power of 1/2, because the square root of some number is the same thing as that number raised to a power of 1/2. So when I find my derivative for my f prime of x, actually, I will find it in a moment. Actually, let's deal with the negative 6 over x to the 4th. It's like the negative 6 over x to the 4th, this part. I'll be using this rule right here, and I'm going to rewrite this as 6x raised to the power of negative 4. And so basically what I've done is I've rewritten these so that now I can find the derivative using the power rule. Like I've rewritten them so that they look like the power rule, like a power rule problem. And so I'm going to go ahead and do my little, power rule now. So exponent drops to the front. So for the first one, I end up with, for my derivative, 1/2 times -2 x, get rid of this, x raised to the power of 1/2 minus 1. So you always subtract 1 from your exponent. And then minus, and then I apply my power rule here. And so I will have -4 times 6x to the -4 minus 1. So notice with the first term, the one written in green, notice we have 2's that we can cancel. So I'll cancel those out. And I end up with just a -1. That negative is still there. X to the -1/2, because 1/2 minus 1 is -1/2. And then notice we have a double negative here, so that's plus. And then 4 times 6 is 24. X to the -4 minus 1, that's -5. And then, so this is actually our derivative, but in the problem, they ask us to write the answer without negative exponents and without fraction exponents. And in this case, we have both. So we're going to go back to our algebra rule and rewrite this so we don't have any negative or fraction exponents. So first of all, the negative part is handled by this right here, right? If you have a negative exponent, you can rewrite it as positive by sticking it in the denominator. So that's what we're going to do. So we'll say this is -1 over x to the power of +1/2 plus 24 over x to the power of +5. So stick them in the denominator to make them positive. And then last of all, because we want no fraction exponents, we're going to use this rule again, just kind of like go backwards from where we started. So we're going to rewrite it as a square root, that x to the 1/2. So we will end up with -1 over square root of x. And then we can just bring the other part down because that one doesn't have anything involving a fraction. So we're done. This is our answer. I'm going to go ahead and write it in, well, type it in, see if it's correct. I entered it and it was correct. So I'm happy, happy, happy. So by the way, if it doesn't say that they don't want fraction or negative exponents, you can leave it the way we first got the answer without rewriting it. But if they say they don't want fraction or negative exponents, make sure you don't have fraction or negative exponents. Let's look at number 5. So number 5 says, if f of x equals 4x squared minus 7x plus 2, find f prime of 5. So what this means, first of all, is like if we're asked to find f prime of a specific number, like in this case, what we want to do is first find f prime of x. So that's like what you first want to do. And then once you have your f prime of x, then you can plug in 5 for x. So let's find f prime of x in this case. So let's use our power rule. So like the 2, notice that drops to the front. And you might notice that you start to do this in your head, like the more you do these. So far we have f prime of x equals 2 times 4, x to the 2 minus 1, and then minus, next, if you just have 7x, that's the same thing as x to the first power. So it's like this 1 drops to the front. And I end up with 1 times 7x to the 1 minus 1. Now, I want to talk about the 1 minus 1 right now. So let's just take a moment to talk about this 1 minus 1. If you have 1 minus 1, that's equal to x to the 0, right? I'm trying to write a 0. That is not a good looking 0, is it? That's a mess 0. That's what that is. Here, I'm gonna write a decent 0 right now because I'm using this little there. That looks like a good 0. So and then any number raised to the power of 0, you might remember this, as long as it's not 0 itself that you're raising to the power of 0. Any number raised to the power of 0 is just 1. And so so for the derivative of 7x or negative 7x, you actually just end up getting negative 7 times 1, which is just negative 7. So that actually will help us understand for finding the derivative of just the 2 here at the end. That 2, you can think of this 2 as the same thing as two times x raised to the power of 0, because again, x to the power of 0 is just 1, and 2 times 1 is just 2. So 2 is the same thing as 2 times x to the power of 0. So if you're finding the derivative of this, think power rule. Notice the 0 would drop to the front, and you would end up with 0 times 2, x to the 0 minus 1, which I really don't care about because 0 times anything is just 0. So that's actually a new rule, and but it's directly from the power rule, and it just says that the derivative of a constant is always going to be equal to 0. So that's a rule to keep in mind. Anytime you're taking the derivative of a constant, you get 0, which, by the way, makes perfect sense. Because if you think about it, if you were to graph a constant, you would get a horizontal line, which means the tangent line to that is going to be horizontal. And you might remember from algebra, horizontal lines have a slope of 0. So, and the derivative is the slope of the tangent line. So if you have a constant, that means you have a horizontal tangent line, which means the slope is 0. So something to keep in mind. So for this part, for the derivative of the 2, I get to just put 0. Isn't that nice? Yes, it is. Yes, it is. Okay, so I'm going to get rid of a bunch of stuff that I've written. Just to... And now, what do I get to say? What do I get to say? That my derivative f prime of x is 8. I have a hard time writing. Here, I'm going to type this. 2 times 4 is 8. X to the first power, which if you have first power, you don't have to write it, right? And then minus 7, because x to the power of 0 is just 0, and then plus 0. We don't have to add the plus 0. So this right here, what I just typed, that 8x minus 7, this represents my derivative. F prime of x is equal to 8x minus 7. So when they ask us to find, which, you know what, before I talk about that, let me just say one other thing. If you want, like, you don't have to, but a lot of people just do this in their minds kind of naturally. you can think of us as having seen a new rule, just that if you have the derivative of a constant times x, like, you know, the -7 times x like we had, that derivative is always just going to be the constant itself. Because like, if you use the power rule on just x, it's like x is raised to the first power, right? That one comes down, and then you take one away from one to get your new power. You get 0, which equals 1. X to the power of 0 equals 1, I should say. And so you just end up getting c. So that's just another rule. I mean, that people kind of, I don't know, kind of do naturally after some practice. So this is, by the way, for both of these cases, c is a constant. These rules that I just wrote down. C is a constant. Okay, so I just found out that f prime of x equals 8x minus 7, and they're asking us to find f prime of 5. So what you're going to do here, once you find your f prime of x, then you're going to plug in five for x. So that's what I'm going to do here. So I can say my f prime of 5 equals 8 times 5 minus 7, which is 40 minus 7, which is 33. And that 33, that's our answer. So I'm going to go ahead and enter that. Right here, that's f prime of 5. So we've gotten part of the answer done, part of the problem correct. Next, they say use this to find the equation of the tangent line to the parabola, this parabola that we're given at the point 567. And then they say that the equation of the tangent line can be written in the form y equals mx plus b, where m is, and guess what? Once you found your derivative, you found the slope of the tangent line. M represents slope, right? So your answer for f prime of 5 is also going to be your answer for your m. Again, that's because the derivative is the slope of the tangent line. So whenever you're finding a derivative, you're finding slope of the tangent line. M represents slope. And so that's your answer for this one, for this part right here. And then the last part, they're asking us to find out what B is. And this is where you go back to your algebra, where you're trying to find the equation of a line. And we're given this point, 567. So we'll go ahead and find the equation of the line given this point. And we know that the slope of our line is 33. So we can find out what the B is. So we'll go ahead and do that. I'm gonna get rid of all my drawings now so we can have a clean sort of page. And so we're going to use y equals mx plus b. We know our m is 33. And then we're given this point right here, 567. So in this point, the 5 represents x, like, you know, an ordered pair. And the 67 is y. So I'm going to plug in 67 for y, and then 5 for my x. And now I just have to find out what b is. Like, b is my only unknown at this point. So let's use the calculator. See, I'm going to go to the calculator. 33 times 5 is 165. So what I have is, at this point, is 67 equals 165 plus b. And to get b by itself, I have to get rid of the 165. So I'll subtract 165 from both sides of this equation here. So I'll say 67 minus my answer, 165, and I get negative 98. So these cancel, and I get negative 98 equals B. And this is my answer for the last part. Nice, huh? There we go. Okay, let's talk about the other 3 rules that I mentioned at the beginning of this lecture. So I talked about how, where is it? Yeah, we're gonna look at derivatives of e to the x, sine of x, and cosine of x. I'm just gonna give you the rules for these derivatives, and the proofs, I posted proofs of those. All of these rules I posted proofs of. Again, if you go to modules and go to the very end, you will see proofs of these rules. So proof of for the rule for a derivative of e to the x, and proof for the derivative of sine and cosine. So if you want to see the proofs, take a look at those. But right now I'm just going to write them down for you. I mean, I'm going to write the rules for you, not the proofs. The proofs are very long. Well, the proof for sine and cosine is pretty long, very long. It's like an hour or something like that. E to the x isn't that bad, but I want to use this time for practice. So the derivative of e to the x, and by the way, the proofs are just if you're curious about it. You don't have to learn them, but it's just if you're curious about them, feel free to watch them. That's why I post them. They're like that's like the big joy of a mathematician, to prove a theorem, right? So anyway, so here's one of the rules. It's that the derivative of e to the x is just e to the x. E to the x is a really special function because it is its own derivative. Here's another rule. The derivative of sine of x is equal to cosine of x. And the derivative of cosine of x is negative sine of x. So let's just practice using these rules a bit. So something like problem number 9, where it says f of x equals 6 sine of x plus 2 cosine of x. So we'll just keep in mind again that the derivative of sine of x equals cosine of x. And I'm trying to write a D. You see how much I struggle with writing on the screen. There's a D. And then the derivative of cosine of x is negative sine of x. So we're going to use these rules right here. And so for the first for problem number 9, the first term, where we have 6 sine of x, it asks us to find the derivative, and we get to say 6 cosine of x. They open parentheses when I press x, so make sure you close the parentheses. And then plus 2, and then the derivative of cosine, we know is negative sine of x. Close your parentheses, and we're done. That's it. That's all. It is more common. So if you see 2 times negative sine of x, that is the same thing as negative 2 sine of x. So I should say that it is more common to write, it would be more common to write your answer like this. Minus 2 sine of x, like that. That's more common. And then from here, to get the f prime of 3, really all you have to do, remember what we did in the last problem? Like we found f prime of x and then we plugged in 5 for x. So for this one, I just copied and pasted because what I'm about to do is I'm going to plug in 3 for x. So I just copied and pasted because I know I'm about to just plug in 3 for x. So that's what I'm going to do. I'm going to replace these x's with 3's. And there we go. And we're done. So that's that. Let's do another one. I'm going to get rid of these pictures. I mean, my writing. Let's do one that has E. So let's look at number 12. Number 12 has an E in it. So it's asking us to find the derivative and then find f prime of 3. So for the first term, you notice the 2x to the 5th. Use the power rule. So the 5 drops down to the front. And I end up with 5 times 2. And you might be doing this in your head at this point, right? And just going straight to, that's 10x to the 4th power, because you know you're multiplying the 5 times 2. And then you subtract 1 from your exponent. And then for this part right here, this part is like the easiest part because the derivative of e to the x is just e to the x. Like, so you don't have to change anything. It's just minus 5 e to the x, and that's it. So, so for this first part of the problem, for your answer, you get to just put 10x to the 4th minus 5e to the x. There's your answer. And then for f prime of 3, do the same thing I did for the last problem. I'm going to copy this. I know I need to plug in 3 for x. And so I'm just going to replace my x's with 3's. And then I'll be done. There we are. Next, for the next part of this problem, they're asking us to find the second derivative. So I'll just explain the second derivative. The second derivative is the derivative of the derivative. So here you have the definition of the second derivative. Second derivative is the derivative of the derivative. And we have lots of different notation for writing second derivative, and they're all written here. So the first one, we read this as f double prime of x. This one's really popular. The second one we read as y double prime. This one is also very popular. And then these two are less popular. And you just read them as the second derivative of y and the second derivative of f. So since the second derivative means the derivative of the derivative, what we're going to do is find for this first part, for this problem number 12, we take our first derivative and we need to find the derivative of what I just circled. So we're going to apply the power rule again. And I get to say f double prime of x equals 4 times 10. Again, you might be doing this in your head at this point, times x to the 4 minus 1. So if you're doing it in your head, you went straight to 40x cubed. And then minus, and then the e to the x part, again, that's the nice one. We don't have to do anything to that because the derivative of e to the x is just e to the x. So we end up with, for our second derivative, this 40x cubed minus 5e to the x. And then we're asked to find f double prime of 3. Once again, I'm going to copy this and paste it. But if I put this in the calculator, I would just get an estimate because of that e. That's just going to give me an estimate in the calculator. So this, what I'm entering right now, is the exact answer, which is so much nicer. So yeah, let's look at one more example, and then hopefully you'll feel ready to do your homework. Let's look at, I wanted to look at this example, number 11, because this talks about velocity and acceleration. So I'm just going to switch over to the iPad to discuss these concepts. So I just wanted to remind you of these concepts from algebra on the left side of the screen right here, that when you find the slope of a line, it can represent just rise over run, right? Like that's how we learn what the slope is in the beginning, like when we first talk about slopes. But in regards to like the world or things that are happening in the world, the slope can represent the average rate of change for some situation, or really specifically average velocity. That's a rate of change that we're all familiar with. So like if I drive 100 miles in 2 hours, we would say that my average velocity is 100 divided by 2, which is 50 miles per hour. So that is a slope, that 100 over 2. It's like the 100 is the rise and the over 2 is the rise over run. So again, 100 over 2 gives me 50 miles per hour, right? If I drive 100 miles over a period of 2 hours, that's 50 miles per hour. That's if the x-axis represents time and the y-axis represents distance, right? Distance over time. What calculus does is it allows us to be more specific. So I'm saying, like with my algebra, I drove 100 miles in 2 hours. That means my average velocity was, this is an average velocity, is 50 miles per hour. Even though my average velocity was 50 miles per hour, though, that doesn't necessarily mean that I was driving 50 miles per hour the entire 2 hours, right? I could have been driving 60 miles per hour at some points of the drive. At some points, I could have been driving 80 miles per hour. At some points, maybe I was at 10 miles per hour. So like just what, so at various times of the drive, I'm not necessarily going 50 miles per hour. I could be going other velocities. And to find those other velocities, we use calculus for that. And the idea you might remember from chapter 1 and section 2.1, the idea is that we let, like with calculus, we let this point that we're using to find the slope, that second point, we let it approach the first point. Like we let it get closer and closer to the first point until we end up with this situation right here. And like the closer and closer we get to the first point, the better our estimation is for instantaneous velocity. And that process of getting closer and closer to the first point and then finding the slope of the line that you get from that first point, that process is finding a derivative, because this line right here is the tangent line. And so the derivative, that's the slope of the tangent line. You can also think of that as the slope of the curve. And then in terms of everyday life, you can think of it as instantaneous rate of change, and specifically instantaneous velocity. So if you have a function that represents the position of something that's moving, the derivative represents the velocity of that object that's moving. So if f of x is a position function, it represents the position of an object that's moving. F prime of x represents the velocity of that object, as in the rate of change of distance over time. My iPad's acting strange. Here, let me rewrite that. And then the second derivative, or the derivative of the derivative, that represents rate of change of velocity. Like velocity is rate of change of the object that's moving, right? And then the second derivative represents the rate of change of velocity. So if you think about changing velocity, like the rate of change of velocity, if you think about what you do, like if you're driving your car and you want to speed up, you want to change the velocity, what do? You press the accelerator. And so the second derivative represents the rate of change of velocity, or in other words, acceleration. So this is something to keep in mind, that your first derivative represents the velocity of an object that's moving. And then the second derivative represents acceleration. So keeping that in mind, we can look at problem number 11, at least part of it. We'll look at part of number 11. So first of all, it says let s of t equal this function. And then it says, and it's the equation of motion for a particle. So that means it's a position function of a particle that's moving, right? And then it says find the function for the velocity, which is telling us to find the derivative. So this is asking us to find fs prime of t. And so we will go ahead and use our power rule. So like the 3 drops down to the front. This time I'm going to do it in my head. 3 times 4 is 12. And then we have t, and then take 1 away from our exponent. So our new exponent is going to be 2, because it was 3. 3 minus 1 is 2. Next, we'll have plus, and then this is 18t squared. 2 drops down to the front. 2 times 18 is 36. So I will have 36. Oops. 36 t to the first power. So if your power is 1, you don't have to write it, right? And then the derivative of a constant times x is just the constant. So I get to just put negative 120. Because this would be 1, like again, if your power is 1, you don't see it, right? This is just t to the first power. And if you imagine that 1 dropping to the front, you'll have 1 times 120. And then t raised to the power of 0 is just 1. So 120 times 1. So we get that. I'll have you try the second part for yourself. It says, where does the velocity equal 0? So basically you want to take the 12t squared plus 36t, whatever you got for your first part, set that equal to 0 and solve for x. So you can either solve this by factoring or the quadratic formula. I think you can factor it. I'm assuming you can factor it looking at it, but I haven't. I'm not totally sure, but yeah, I bet you can factor that. Oh, yeah, and they give a hint. Factor out the GCF. So like in this case, I would factor out a 12. Okay, I'll go ahead and do it since it looks like I can do it kind of quickly. I don't want this video to be too long. And then I look for two numbers I can multiply and get -10, add and get 3, +5, and -2. Right? Is that right? 5 times -2 is -10. 5 plus -2 is 3. And then set each factor equal to 0 and solve for x. So I end up subtracting 5 here. So I get t equals -5 and then adding 2 here to get t by itself. I get t equals 2, or sorry, to get t by itself. And so I get t equals -5 and t equals 2. So, oops, I don't want that. T equals -5 and t equals 2. And then for the last part of this, it says find the acceleration function. I'm going to get rid of all my writing. So for the last part, it says find the function for acceleration, which means we need the second derivative. So we're going to go to the first derivative and use the power rule on that. So like 2 drops to the front, 2 times 12 is 24. So I will have 24t. And then apply, the rules I was talking about. Like if you have a constant times your variable, the derivative is just going to be the constant. So plus 36. And then you remember the very last, not the very last, I guess maybe the third rule that I talked about today, which is that the derivative of a constant, I think it was the third rule or maybe the second rule, just that the derivative of a constant is always equal to 0. So the derivative of -120, that's just 0, which means I don't have to write anything here. I don't have to write +0 or anything, because when you add 0 or -0, because that won't affect the number. So try your version of the homework. If you have questions, come to our work session. Take care. Bye.